So, hello everyone. My name's Alex Chircop, and I'm from StorageOS. And my co-presenter here, Jared, is from Upbound. And we're going to talk a little bit to give you guys an intro to container storage. Some of the stuff you might be familiar with, some of the stuff might be new. Feel free to interrupt and ask questions as we go along, and we'll cover things as we go. So, Quinton very helpfully in his first slide kind of covered what I was going to cover in my first slide, which is why do we need persistence? Because, as Quinton said, stateless applications are kind of a myth. I kind of go one step further and say there is no such thing as a completely stateless application or a stateless architecture. Everything needs to store state somewhere, whether that is in your own system or it is in a service or it's in a database or something, but somewhere, we're always going to be storing that state. And when it comes to storage systems for these sort of cloud-native architectures, we have a bunch of challenges. The first challenge being that we don't want to have storage pets. So what do we mean by that? So if you're familiar with containers and Kubernetes, you have this concept of pets versus cattle. Pets being things that you nurture and are very personal and are very special, and cattle that are kind of disposable and have a lot of homogeneity between all of these different options. And what we really don't want to do is have storage systems for persistent storage where your systems are tied to very special hosts or very proprietary systems. You don't want storage pets, effectively. The second thing is we've made a big effort to make containers immutable and portable, and put all the dependencies of an application inside a container. This means you can now move your container about, and your containers are platform agnostic. So you also want to store. Another challenge is you also want storage to be able to follow your containers, whether it is across different platforms or different providers, or even just different systems within your environment. And the third challenge with persistent storage is humans are fallible, right? So a large chunk of what we're trying to do with orchestration is make your processes declarative and repeatable. And in order to do that, you also have to have all the other components in your systems being declarative and composable too, such that they're automated. If we have humans constructing individual bits of infrastructure or defining operations that need to happen as part of your application workflow, you are going to have errors, you are going to have downtime because of that. So we put a little bit of thought into this a couple of years back now, actually, and came up with these 8 principles of cloud-native storage. So these are the sort of things that you need to think about when you're looking at different options in your environment. So Quinton talked about some of the different attributes that your storage system needs to look at. These are the 8 things we think cloud-native storage should really identify with. So the first thing, which is completely different with cloud-native storage, is that cloud-native storage needs to be application-centric. We're moving away from an environment where storage was presented to operating systems or hypervisors or VMs, and that storage was now tied to that individual node. But not only that, it was tied to wherever that node had its storage fabric, or whatever connectivity those specific nodes had to that storage system. So you now have this really complicated environment where an orchestrator has to bifurcate where the application can run and where the storage actually is, and then try and make those decisions. But what you really want is you want storage to be presented to applications, and as the application moves, the storage can move with the application. A lot of what we're talking about, the portability, kind of means that you want your storage to be platform agnostic. You don't want to be locked into individual data centers, individual cloud providers, individual colo providers, etc. The storage platform needs to be able to run anywhere, and it needs to be able to be upgraded and scale in an undisrupted manner with the rest of your applications. we talk a lot about orchestration in cloud-native environments, and orchestration kind of means you want your systems to be composable, declarative. So in much the same way that today you can say, I'm going to compose my application, and I'm going to say it needs all of these different libraries and all of these different application dependencies. And then I'm going to also define what CPU requirements and what memory requirements you have, and perhaps what ports you need and all of these other things. You also want to be able to declare and compose your storage requirements. So you also need to be able to say, my application needs this type of storage with these type of attributes. And an orchestrator should be able to dynamically provision that for you. For an orchestrator to dynamically provision this, what you're really looking for is a storage system that's API driven. So once you have an API driven environment where storage resources can be provisioned, they can be moved, attributes can be changed dynamically through an API, and everything is declarative with an orchestrator, you now have self-provisioned storage. You have an environment where developers can define what their application needs, and the storage can go and create and provision those volumes as needed. In cloud environments, in managed environments, in orchestrated environments, you have you are aiming to get a better level of utilization. So in general, you're going to have more applications sharing more nodes. You're going to have more security requirements, more multi-tenancy requirements. So it's very important that your storage system also integrates natively with the security infrastructure that your orchestrator supports. So whether that's things like namespaces to partition off applications or different business units in your organization, for example, or things like RBAC and ABAC, or even things like encryption to protect your data in public environments. I put Agile in here. It's super cliched, and I'm going to say that up front. The reason why I put Agile in there is because in orchestrated environments, it is a fundamentally different system compared to traditional environments. You have a lot more moving parts. Nodes come and go, nodes get upgraded. Perhaps you have automatic scaling set up in your environment. So your storage system needs to be able to live in that sort of environment where lots of things are changing very dynamically under the covers. They need to be able to resize, they need to be able to upgrade, and they need to do all of this non-disruptively. And that kind of takes us to the next 2 points, which is performance and consistent availability. So in these sort of dynamic environments, if your storage system is not built for that, then your storage system is going to is not going to be able to offer deterministic performance and deterministic performance under different levels of failure. And this is key. If you ask some people, they'll say, well, we need the fastest performance for everything. In which case, go for some super local storage, some super fast local storage, some big SSDs, and run your analytics there, if that's what you really want to do. But for the most part, if you're running transactional systems, if you're running interactive applications, what you really need is deterministic performance. Your developers expect a certain number of transactions per second, or they expect a report to run in a particular amount of time. And they expect that to happen the same way every day, rather than something taking 4 or 5 times the time just because a node failed that particular day. Because these things happen more often. So this kind of takes us on to the next couple of things, which is, out of all of the attributes that you see in a storage system, different storage systems have different methods of accessing them, and they have different methods of orchestrating. Quentin talked about some of the different attributes, whether that's the topology, where the storage is instantiated, etc. But a large proportion of what people think about is how you access the storage, and this is what we mean by a data access interface. So an orchestrator will be talking to the control plane of a storage system, and that will be used to make available different types of storage. Those different types of storage typically fall in 2 major buckets. So we've in a CNCF storage white paper, we've kind of classified these as volumes and storage that you access through an API. So volumes might be the thing that a lot of people are familiar with in terms of actually having a file system or a block store or perhaps a shared file system like an FS, where you're actually storing files somewhere. And this can be used for your databases perhaps, or web services, or in fact anything that needs a file. An API storage is storage where you're accessing that as a service over the network. So broadly speaking, the most obvious the most obvious example of an API store is an object store. But similarly, as Quinton mentioned earlier, things like key value stores, but also databases are viable ways of storing systems. One thing that's really, really important, though, is that when we compare different attributes of the storage system, we often use the access interface as the defining method of access, or as the defining attribute, because people have a certain perhaps understanding of what a file system can deliver versus an object store, for example, or what a block storage system can deliver. But what we need to remember nowadays more than ever, especially in cloud-native environments, most storage systems are created in lots of complex layers. And apart from some of the attributes that we talked about, like the topology or where it's instantiated, or some of the consistency or performance requirements, we also have to realize that the presentation layer, the thing that the workload actually accesses, is often also just another layer. So for example, you could have a distributed file system that's offering a block store interface to the end user. Or you might have an object store that's offering a file system interface to the end user. So when you're looking at those sort of things, you need to remember that things like the latency, the performance, and the different attributes of the system are actually defined by the underlying layers. That's how the data is going to be protected. The topology of that underlying layer is going to define the latency of that system, for example. And we shouldn't always just worry about how you access that, because that doesn't always define, that's not the end defining factor anymore. Now I'm going to pass on to Jared, who's going to talk about the orchestrator interfaces.
I think I got it. Oh, yep, I got my own microphone here. I think Alex has met our accent quota. Maybe a little Pacific Northwest, I don't know. Yeah, so I'm Jared Watts. I'm not wearing my credentials right now, so because it would interfere with the microphone, but I promise I am who I say I am. So, so similar to what Alex was just talking about with the data access interfaces, we also need a way for our container orchestrator to be able to communicate with our underlying storage system and make things happen. This diagram may look a little familiar from about 45 minutes ago or so in Quinton's deck, so we're not going to spend too much time on it. But the important part here that we want to look at is, so we see that on the right side of the diagram, we have arrow C there, and that's what Alex was just talking about, how our workloads, our containers, access the data and actually use it, read and write bytes. And so on the other side, the left side of the diagram, though, we have these interfaces for how our container orchestrator can make things happen. A good example of that would be when a workload needs to have a volume so that it can start consuming that and persisting its application state to that volume. We need our container orchestrator to talk to the underlying storage system through these control plane interfaces to make that happen, to provision the volume on demand for us. So we're going to go into some more details about what some of these interfaces look like CSI and flex volumes. And I think we're on the very next slide, actually. So let's go ahead and look at that. So for container storage, we have a couple of different control plane interfaces. The first one we're going to talk about is the native in-tree volume plugins for Kubernetes. Now, there's a very broad set of coverage across a lot of cloud providers and a lot of storage vendors that these in-tree volume plugins give the ability for those storage systems to provide their data services to your workloads, to your containers and pods running in Kubernetes. The only real downside I see to that, though, is that they live in the source tree of Kubernetes. So in order to ship new changes, bug fixes, new versions, it's tied to the Kubernetes releases and the Kubernetes process. So it can be a bit constrictive there. The next one here is basically how the Docker runtime does volume plugins, this interface here, so that your storage system can provide storage on demand to containers that are using the Docker runtime. So flex volumes, we got the opportunity on the Rook project to write a flex volume, and it's a great way to connect a storage system into Kubernetes, and it gives you that ability to, since it's out of tree, it's not tied to Kubernetes releases at all. You can ship changes to it or bug fixes on your own time, your own process. So that's nice. But this is a deprecated interface now in favor of CSI, the container storage interface. And we're going to have an entire panel this afternoon with some of the brilliant minds behind CSI that they're in this room right now. But basically, just the real quick gist of CSI is that you can look at it as a universal interface to connecting to a bunch of different container orchestrators like Docker, Mesos, and Kubernetes. So you write your CSI plugin for your storage provider once, and then you can reuse that across all those container orchestrators. So it's very nice to be able to have that reach now. So let's talk real quick about how Docker does storage. Oops. So a quick thing to remember is that a container image is basically just stacked layers, data layers. And so when a container is running, it's writing its data to a separate layer, a container layer. That's you can think of it as being ephemeral. It's not persistent. So when that container is shut down, all those reads and writes that the container had done to its local file system are gone. They're not persistent. So if you want data to live outside of the lifecycle of the container itself, then you need a solution for that. So in Docker specifically, there's two ways that we can talk about doing that. One of them is a local named volume. So you can create a volume that's backed by the host's file system, and the container can read and write to that. And when that container goes away, that data still lives on the host file system. And another container, a second container, can start up later on and consume that same Docker volume from the host file system and reuse that same data. So that's one means of achieving persistence. But the downside here is that it's only on a single node itself, which leads us to the Docker volume plugins themselves, where this is, as we're talking about, that control access interface to be able to connect a storage provider to Docker through these volume plugins. And this is great because this is persistent storage across nodes in the system. So if a workload is running on one node and goes down and is moved to another node, you can still access that same data. It's not constrained to specifically having to be on the same host. And these are some commands about how you can take advantage of these plugins and use these plugins, but we'll go ahead and skip through that a little bit right now. So now let's move to Kubernetes. We're here for Kubernetes this week. Let's focus on that now. So there's two main flows and how Kubernetes deals with storage for pods. The first one we're going to talk about is static provisioning. And so in the static provisioning flow, the administrator, what they have to do is they have to manually create these persistent volumes ahead of time. They create or register these volumes into a pool. And then when an application developer comes along and needs a volume for their pod, they can claim a volume out of that pool. And so this has the obvious downside of, the administrator has to be on that path. They've got to manually create these volumes and have them ready for the application developers or the pods to be able to use them later on. If all the volumes that the administrator had declared or created or registered, once they're used up, there's no more left, right? So the pod wouldn't be able to get access to a storage volume and be able to run its workload. So that is in contrast to dynamic provisioning, which I think it came out in maybe 1.6 of Kubernetes. I can't remember exactly. But it is much more flexible in the sense that the provisioning or the creation of a volume for a pod is done on demand at runtime. So instead of creating specific volumes by the administrator, what they do instead is they create what are called storage classes. And you can think of those as being like a blueprint for how storage will be created when the pod actually needs it. So we see here that our administrator has created two storage classes, one as a sort of a fast profile. This will be using high performance storage, and then a standard storage class as well for just normal, middle tier storage performance. And so this time, in contrast to the static provisioning flow, the application developer comes along with their pod, and they need a volume for their pod to store their state in. And what's going to happen this time, though, is that when the pod or the developer here claims a volume, on demand, dynamically, a volume will be created for them using these storage classes that serve as that template or that blueprint for them. So the developer here says, I want a fast storage class, or sorry, a fast volume, and the template or the blueprint for the fast type of storage will get used to on demand generate a persistent volume that will then get bound to the pod and used by the developer. So that's really useful where instead of having to manually upfront create all of these volumes by the administrator, they'll be done on demand and when they're actually needed. And so you don't run out of volumes until you run out of space in your entire storage cluster. So I think we might be using an old deck that's missing a slide at the end here. But I wanted to talk about a couple of advancements by the Kubernetes community recently. So over the past few releases, and I want to give a special shout out to the special interest group for storage in Kubernetes, the SIG Storage. They have done some amazing work. Some brilliant minds over there that have some great features that have been implemented over the past, for lots of releases actually. But so some of the new things in storage for Kubernetes are, let's see, I think there's like a topology-aware scheduling is pretty interesting because so when you have a cluster that spans multiple zones, you could end up in a scenario where your pod gets scheduled to one zone and your volume is provisioned in a different zone. And so therefore the pod can't consume that volume. They can't talk to each other. Oh, sweet. And the slide's coming up. Nice. Thanks, Alex. So in that situation, it's a complete waste of those resources. Your pod can't actually consume the data. But instead, with topology-aware scheduling, you can be a little bit smarter about that. That pod, the volume will be provisioned in the same zone that the pod is going to get scheduled to, and so therefore the pod and the volume can bind, they can talk to each other, and it'll be useful in more complicated clusters that have more difficult or complicated topology. So volume snapshots is another cool feature that's coming out recently that basically gives the ability to represent snapshots and restore and backup operations with the Kubernetes API. So you'd be able to, from the kubectl command line or other tools, to kick off snapshots or even restore, create a new volume as a restore from an existing snapshot. So integrating backup and restore into Kubernetes is really great to have that. I think a lot of people have been asking for that for a while. Local persistent volumes are pretty neat because this gives the ability or the smarts in Kubernetes to manage entire disks now. If you had a stateful set, you would normally before kind of have to use some volume claim or some dynamically provisioned volume as the underlying storage. And now we have the machinery to use an entire disk. So distributed storage systems like Gluster or Ceph that are smart about managing disks and building a distributed storage solution out of those disks now have that building block to directly use the entire disks. Mount propagation is cool because that allows you to share volumes across containers and pods. So when you mount like from the host file system, you do a bind mount into a pod. This mount propagation allows changes that are done or writes that are done to that volume to be reflected back into the host file system, meaning that another container can do that to bind mount to that also, and they basically be sharing a volume. So that's a new feature. And then the last one here, since we already talked about topology-aware scheduling, is raw block volumes. So when we were that dynamic volume provisioning flow that we were talking about in the slide previously, when that happens, before this, what would also happen is that it would get a file system formatted onto it, which provides another layer of a layer to go through to have that file system. It's nice from a flexibility standpoint where the application has a consistent file system like ext4 or XFS or whatever to be able to write to, but it also puts that extra layer there. So now if an application is smart enough to know how to deal with a raw block device, that a dynamically provisioned volume can just surface just the raw block device with no file system on top of it, and that helps out with performance. And so now I think that's the actual end of the presentation. So we're open to some questions for however much time we have left, according to Lisa.
You can put the, okay. Any questions? Yes, hang on. Okay.
How do we get access to all these decks?
See, I told you it's going to be good content. You're going to want it. We are recording everything. So, keep it clean, everyone. Forgot to mention that at the beginning. I don't want to have a long editing process before I put things up on YouTube. So everything will be on YouTube. We'll probably link to it from our cloudnativestorage.com website that we now have. And we will also put a slide share up there as well. So once we get them all done and PDFs and everything, we'll put the slide share. So just keep checking cloudnativestorage.com. Any other questions? Yes, hang on. Does anyone have any Advil, by the way? Anyone? Any other drugs? Anything?
Hi, I see you from StorageOS, right? So I just checked your website, but I didn't see any like a child version or something that to play around with it. So do you have any like open source version where I can just place on my environment on a Kubernetes cluster and play around with it, or should I just use your like kind of enterprise version?
So there is a completely free version, and I think you'll find there are free versions of all the people who are sponsoring this this event. So there's a free version available of StorageOS, and you can download it. It's just in Docker Hub and install it.
Any other questions?
So for the topology-aware provisioning, what drives that? Is it just the location of where the pod has been scheduled creates the volume, or can the volume actually anchor where where the volume is actually created? Can that drive where the pod is scheduled?
So effectively, it works both ways. It's possible for the location of the topology of the volume to define where the pod gets created, but also the other way around for Kubernetes to tell the storage system that we're going to be provisioning somewhere, and please storage system to make that available there.
Okay, I can take one more question, and then we have a coffee break, or just a break, and then the next presentation after that. So, any more questions?
Yeah, sorry. One more question. Does your StorageOS support bare metal, like a local disks or something like that, to manage like bare metals? Okay. My point is, for example, you schedule a pod, for example, on one underlying host machine, right? But if it's doesn't know how to keep this pod running exactly on this machine, for example, through the stateful set, but I want to keep my data on this particular, like in the Kubernetes 1.10, it's been introduced local volume storage. So does it support it the same way or different way?
Hang on.
So effectively, you'd use a daemon set, or we can use an operator to do this. And you'll find that, again, a lot of the vendors here will be supporting similar sort of functionality, where there is a level of intelligence during the deployment of the tool to make sure that those things are taken care of.
Yeah, and I think in general, though, too, that most of these distributed storage systems, the storage they're providing for your pods is independent, really, of what specific node in the cluster your pod is getting scheduled to. So when we're talking about those data access interfaces where the pod or the workload can talk to the storage system through an API or through a volume, the storage systems, they have integrated into Kubernetes through volume plugins and then also through those native APIs where whatever the node that your pod is running on, it will still be able to talk to the distributed storage system that you can think of it as like a fabric or a mesh that spans all those nodes in the cluster. So it's not always important which node your pod lands on, as long as it's in the same zone where there's network connectivity across those nodes. So that's important to remember.
And I want to remind you, we have the 8 of us standing at the high tables in the back, and we're happy to answer more questions. I know we have a lot of customers running on bare metal doing exactly what you're asking about. And so we've got people in the back that can talk about it. I'm sure probably we all have good examples we can walk you through. So remember, we're here for you. That's what the high tables in the back are for. So we want you to use the breaks and the networking sessions and the lunch so to be able to talk to the folks from these 8 companies, and we can spend some one-on-one time with you. So we have that built into the schedule. So don't forget that. Did I mention we have lunch coming in? We do have lunch coming in. I forgot to say that this morning. And we tried to make it easy with like bags of, I don't know, sandwiches or things that'll be easy to eat without tables. I realized you couldn't set the whole room with tables. And we do have some vegan and gluten-free options if you're in those categories. Please, we're going to take a 10-minute break now, but definitely come back. We have our next presentation is on day 2, solving a lot of those problems that that we all know are a little bit harder than some of your typical day 1 problems. So we've got a great session on that coming up next. Remember to go to cloudnativestorage.com for the whole agenda, and I'll put it up on the screen here too. So just quick 10-minute break, and everyone give Jared and Alex a warm applause. Thank you so much, guys. Really appreciate that.